So go ahead, Amar.
Okay, thank you very much for thank you very much. You're welcome to this edition, this fifth edition of the Bandoleros on bundles and their application in algebraic geometry. And I have the pleasure for our first talk to present Ugo Bruzzo, Professor Ugo Bruzzo from CISA, and also from Departamento di Matematica in the Federal University of Paraíba. And he will talk about semi-stable Higgs bundles on elliptic surfaces. Thank you very much. Ugo, you can...
So you have to turn on your mic.
The microphone is...
Yeah, whoops, sorry, it was off. Okay. No. Okay, so let me start by thanking the organizers for this invitation, which I appreciate very much. And so my second slide is about the place where we should be now. So it's also a nostalgic tribute. So let's hope to be able to do such things in presence again soon. And so I'm going to talk about some results I got in collaboration with Vito Antonio Peragine. And, you know, over the last few lusters, I've been annoying people about a conjecture about semi-stable Higgs bundles. And actually, this research was motivated, again, by that conjecture. So I will talk about the conjecture later on. And so the fact is that together with several collaborators, we have been able to establish this conjecture on several classes of projective varieties. And then the project we had with Vito was to study this conjecture on elliptic surfaces. And this actually, we didn't prove it. We didn't prove the conjecture in full. For the moment at least, we just have a kind of generic, proof of the conjecture in a generic situation, in a sense I will explain later on. But this also came with some side results about Higgs bundles on elliptic surfaces. I mean, some structural results about Higgs bundles on elliptic surfaces. So now some introduction first about some reminders actually about elliptic fibrations, elliptic surfaces, and then about bundles over elliptic surfaces before moving to Higgs bundles on elliptic surfaces. So till I will talk about the conjecture, we may think that we are working with varieties over an algebraically closed field of a characteristic 0. It is exactly when I shall pass to talk about the conjecture that I will restrict to varieties over the complex numbers. So, so by elliptic fibration over an integral scheme B, we mean the following. It is a proper and flat scheme over B, whose geometric generic fiber So the geometric fiber over the generic point of B is an irreducible complete non-singular curve of genus 1. And we shall assume that B and X are non-singular, and that this vibration, the fibers are at worst, they may be singular, but they are at worst nodal. And actually, at some point, I will restrict B to be a curve, and therefore X will be a surface, an elliptic surface. And the first fact we shall need is the following. The sheaf I wrote here, it happens to be a line bundle. And this, which is line bundle, which is called the fundamental line bundle of the elliptic fibration, happens to know a lot about the fibration, as we shall see. So this will be one of the basic technical tools to study elliptic fibrations. In particular, it is by means of this line bundle that one is able to exhibit a Weierstrass model for a particular class of such fibrations. So we call Weierstrass fibration a pair pi sigma, where pi is indeed an elliptic fibration. We assume the fibers to be integral, and but we also prescribe a section of the fibration. And then what happens is that if you consider this direct image, which I called S3, this happens to be isomorphic to the direct sum of these three line bundles. So we take the projective bundle associated actually to the dual of this vector bundle S3, and then this cohomology, the cohomology of, the cube, the third power, of the tautological bundle, the relative hyperplane bundle, happens to have this decomposition, right? So in terms of the cohomology of suitable powers of the line bundle L, and in particular, this contains the vector space we see here in the bottom of this slide. And if we fix suitable sections, A4, A6, of suitable powers, 4th and 6th powers of the line bundle L, this equation cuts out an effective divisor from P. And the natural projection map that we have from S3 to L to power -3 actually defines a section of this projective fibration, which happens to take values in this divisor, thus defining a section. Of course, X bar fibers over B, this is sigma bar is a section, and the pair X bar sigma bar is a Weierstrass fibration according to the previous definition. And this happens to be, for a suitable choice of the coefficients, the sections AI happens to be a Weierstrass model, namely it exhibits our fibration as a family of cubic curves. Okay, this is from what we see from this equation, the last line of this slide. This exhibits our fibration as a family of cubic curves. So this is the content of this proposition. Okay, but this is exactly what I already said. Okay, so and this is important to make computations. Now, actually, from my presentation, in my presentation, all computations will be hidden, but there are quite a few computations behind it, and many of them are done using this representation of our fibration. So from now, we assume that B is a smooth connected projective curve of some genus G, and we assume that we have indeed a Weierstrass fibration over it with section sigma, and we call D the degree of the line bundle L. Now, if we take, we consider the collection, the subschema of singular points of the fibers of pi, This happens to be a local complete intersection closure subscheme of dimension 0, clearly, and the length it happens to be 12 times d. And what happens is that the fibration has no singular fibers if and only if d is 0. So when d is 0, you get what's called an isotrivial fibration, and we assume that d is actually positive. So we deal with a situation where singular fibers are there. Okay, and a fact that we shall need, again, a technical fact, is that under all these assumptions, if we have a torsion-free sheaf on X, I mean torsion-free OX module, then its image is actually locally free. Its image over the curve B is actually locally free. So this is, small collection of basic facts about the kind of singular, of elliptic surfaces we are going to consider. Now we study a little bit vector bundles on such an elliptic surface. And one interesting and useful fact is that to any vector bundle on X, one can assume what is called the associated spectral cover. And this is going to be actually a curve inside X, which is a covering of the basic curve B. And we assume that our vector bundle is such that its restriction to every fiber of the elliptic surface is semi-stable and has a trivial determinant. By semi-stable, I mean that it is a slope semi-stable with respect to some polarization that we have fixed. And now we construct, one constructs the spectral cover in the following sense, in the following way. It happens that for every closed point in the base curve, we have this natural map, right, due to a disjunction, the evaluation map. And when we restrict this to a generic point of a fiber, this happens to be an isomorphism. And then, and then we define this line bundle. This is a line bundle on B. If we consider the determinant of the evaluation morphism, this happens to be a section of this line bundle, okay? The pullback of mu twisted by this line bundle, r times the associated to r times the section. And so we have the local system, r sigma plus mu star, pi star mu, and the determinant of EV defines exactly a curve inside this linear system, which we call the spectral cover of B. I should say that since later on we shall consider Higgs bundles, this is not the spectral cover or spectral curve of a Higgs bundle. In this, I mean, it's not the spectral cover in the sense of Higgs bundles. So this is a curve inside X, which covers the base curve B, and actually it need not be reduced nor irreducible. Okay. And actually, you know, when we have a semi-stable, so I would like to mention briefly the Bogomolov inequality. So actually, this equation is slightly wrong because what is the discriminant delta V is the content of the brackets, okay? It's this characteristic class. This is called the discriminant of the vector bundle. R is the rank of the vector bundle. And then in general dimension, intersecting with the suitable power of the polarization, we get a number. And the Bogomolov inequality says that when we have a semistable vector bundle or torsion-free sheaf, this number is non-negative, right? Now what happens is that if we consider Higgs bundles or Higgs sheaves, semistable Higgs sheaves, they happen to satisfy the Bogomolov inequality even when they are not semistable as ordinary sheaves. I mean, even when the underlying sheaf is not semistable, but the Higgs bundle with its Higgs field is semistable, the Bogomolov inequality is satisfied. In our case, first we are on a surface, so this power of the polarization is not there. And we assume that C1, that the determinant of V is trivial on every fiber. This makes this square vanish. And therefore, in our case, the Bogomolov inequality for V is simply that its second Chern class is non-negative. And then you see that we were saying that the spectral cover of V need not be reduced nor integral, but actually the fact that it is either integral or reduced puts a lower bound on the value of the second Chern class. So not only these bundles satisfy Bogomolov inequality, but C2 V as a lower bound, slightly different according to the two cases. So you see that it's true that this spectral cover may be, let's say, nasty, but the fact that it's good, is nice, relates to the fact that C2 is big enough. Okay, so we have this property of the spectral cover, which is going to play a role in the following. So, of course, you are very welcome to stop me and ask questions whenever you want, which would be a good idea. Otherwise, I run too much, most likely. So you hear me, right? Because, you know, during these talks, at some point, one gets the feeling that perhaps nobody is on the other side.
Yes, sure.
We hear you and we are awake.
Okay, very good. You are not sleeping because, you know, another possibility is that you sleep and I don't realize that. Okay.
Maybe one question. What happens when C2 equals 0? Regarding
I don't know. Well, no, I know. This is, of course, well, I would like to know, because this is about the conjecture. Because the conjecture is about characterization of bundles whose discriminant is 0.
Okay.
So I can tell you what happens, because this is a theorem which will appear in one of the last slides as a reminder. It's an old theorem. It's very clear what happens for semistable vector bundles, and what exactly happens. The Higgs case is the matter of the conjecture.
Okay, thank you.
So this is the it relates to a property we have called curve semistability, whatever that means. Under our assumptions, C2 equal to 0 will imply that the bundle is a curve semistable. Also in the Higgs case, the fact that also the opposite implication is true is the content of the conjecture.
The conjecture is for surfaces?
No, the conjecture is in any dimension, but it's enough to prove it for surfaces. Because if you know it for all surfaces, then you prove it for all varieties. Because you go up, you make induction on the dimension using the Meta-Ramanathan technique, basically.
I see. Thank you.
So yeah, the important case is that of surface, but all surfaces, of course, all surfaces. What we are able now is to control the situation on classes of varieties, as we shall see at some point in one slide. Okay. Okay, and then we also need to consider a class of bundles that are called regular. I should say that this theory of vector bundles on elliptic surfaces mainly comes from Friedman, Morgan, Witten. Quite a few years ago, they wrote a short series of papers motivated, I think, by geometric engineering in string theory. They made a deep study of vector bundles over elliptic surfaces, and so most results here are taken from there. But this will also overlap with the study of vector bundles on elliptic curve that was made again many years ago, mostly by Atiyah and also from Tu. And so I will go back for a moment to the case when we have just one elliptic curve, which we assume to be integrally complete. So that means that either E is smooth, is regular, or it is singular, in which case it may have one node or one cusp. Okay, and then the Picard scheme, pick 0 of this variety, it's known not to be complete. Basically, what happens that if you want to get a complete compactification of it, which I denoted pick 0 E bar, you need to add a rank 1 sheaf, which is not a line bundle. Because there are, in some sense, sequences of line bundle which approach this object which is not locally free. And this additional object you need to add to compactify is indeed a twist of the ideal sheaf of the singular point, which is not locally free, due to the fact that the point is singular. Now, if we fix something, an element in this compactify Picard scheme, we say that a vector bundle I on E is strongly indecomposable with the Jordan-Hölder constituent lambda if it is a filtration of the Jordan-Hölder type, actually, whose quotients are all isomorphic to lambda. And this homomorphism group has dimension 1. Okay, so this is the definition of a strongly indecomposable bundle with the Jordan-Hölder constituent lambda on an integral elliptic curve. Losing control. Okay. Now, this strong decomposability, it's easily seen to imply indecomposability in the ordinary sense. One can show that if lambda happens to be invertible, any indecomposable, so this is a sort of opposite to the previous statement. If lambda is invertible, any indecomposable bundle with a filtration whose subquotients are isomorphic to lambda is strongly indecomposable. It actually happens to be a bundle of a special kind, namely up to a twist lambda, is a so-called Atiyah bundle of rank R. Namely, it's an iterated extension of the structural sheaf by itself. Okay, on an elliptic curve, the kind we are considering, for instance, if you consider extensions of the structural sheaf by itself, there are only two. The trivial one, the direct sum, and one which is actually the Atiyah bundle E2, which is a bundle of this kind, is strongly indecomposable. And then you can iterate this, keeping on extending by the structural sheaf, and you get the Atiyah bundles of any rank. And then we have a definition: a vector bundle of degree 0 E is regular if it is a direct sum of strongly indecomposable bundles, with the additional condition that all associated lambdas, right, Jordan-Holder constituents, are non-isomorphic. So they must be pairwise distinct.
So here, vector bundle is locally free or just torsion free?
No. I'm identifying vector bundles with the locally free sheaves.
So the non-invertible sheaf on peak 0, can it appear?
Oh, they can.
Okay.
Yeah, but the second statement in this slide, I stated it only for vector bundles.
Okay. Right.
I think it's a correct statement, right, only for vector bundles. While the first statement is true also for non-locally free E, because they may happen to have a finger, right?
Mm-hmm. I see.
Well, no, I'm considering vector bundle from the beginning. Yeah, you could consider a more general situation, I agree. Yeah, but I'm just considering bundles. This is actually what we need.
Okay, thank you.
So again, regularity has something to do with the spectral covers. Indeed, we have this result that if consider a fiber-wise semi-stable vector bundle V. So this vector bundle is semi-stable after restriction to every curve. We assume it has vertical determinant, which means that the determinant is the pullback of a line bundle over the base. And it will have some spectral cover, which we call C. And let's assume that a base point B in B corresponds to smooth points of the spectral cover. Okay, so the spectral cover, we have a finite bunch of points sitting on top of B. We assume all of them to be smooth points. Then the restriction of a V to the fiber XB. The fiber XB is an elliptic curve by hypothesis, so the restriction of a V to the fiber XB is regular. In particular, of course, if C is smooth everywhere, then V is what we could call fiber-wise regular. So it's a regular on all fibers. And again, we shall meet such bundles later on. And now I will state and briefly comment 3 results about Higgs bundles over elliptic surfaces. The first result is the following, that you see in the middle of this slide, I wrote the sequence which defines the relative differentials in our fibration. And from there, you can prove that, well, if you take the direct image of the differentials of X in the middle, the direct image yeah, it's a power. The direct image is a power of the differential of B. And in particular, what happens is that the direct image of the symmetric power gives you the of the differentials, gives you the art power of the canonical bundle of B. As a result, you know, when you consider the hitching fibration, it has a basis which is given by this direct sum, right? The direct sum of sections of the symmetric powers of the differentials. And therefore, this will establish an isomorphism between the hitching basis for B or for the elliptic surface. And this allows, by pullback, to define a rational map between, these are the modular space of semistable Higgs bundles, right, on B or on X. And then the statement is that the pullback establishes a rational map between these two, which covers the same hitching basis, right? Because we identify the hitching basis for B and X. So this is a small side result, which we actually we plan together with Vito we plan to go to investigate more the relation between the modular spaces of the Higgs bundles on B and on X. We think we may have some interesting results. So this is just a first hint of some relation. And I'm not going to deal with this anymore, I think. But now, on the contrary, two things that will be important in the following. So again, we are in the situation we were considering. So we have a Weierstrass fibration over a smooth projective curve, and we have a vector bundle on X. And of course, we know that the Higgs field is a map here in this home space, right? Satisfying this integrability, let's call it integrability condition, right? Of course, we have two things. We have the injection of the pullback of the differential of B into the differential of X. Sorry, I'm just considering that. So we have the tensor by the endomorphisms. So of course, we have this inclusion, and we may call the Higgs fields that are in the group on the left, which automatically satisfy the integrability condition. We will call them vertical Higgs fields. Actually, the fact that we may ask if under some conditions the Higgs field of a Higgs bundle over X is of this kind, and I mean it's vertical. And actually, it happens that under the general assumptions we are making, this is related to the fact that the spectral cover is reduced. And the fact that the spectral cover is reduced is a kind of a generic condition for the spectral cover. So in some sense, the generic Higgs field, we might say, is vertical. And under these assumptions, of course. So the assumptions are that V as a vertical determinant, and it's enough to assume that it is semi-stable on a generic fiber of X. Okay, so vertical determinant, semi-stable, I mean the vector bundle as a vertical determinant is a semi-stable on a general closed fiber of pi, and we assume that the spectral cover is reduced. And this implies that the map up here is an isomorphic, and therefore all Higgs fields on V are vertical. Okay, so we have a characterization of all, of the Higgs bundles that have a vertical Higgs field. So this is first kind of result. And the proof is, a string of computations. So the first line is just the exact sequence of the differentials twisted by the endomorphisms. Then we take direct image. And now we can apply the fact that the spectral cover is reduced. And this implies basically that VB, it's a quite how to say, I mean, heuristically, it's a quite natural result when we restrict our vector bundle to a generic fiber. It is the direct sum of R different line bundles, all of them with degree 0. Right, and this thing here is something I didn't tell before, but it happens that the differentials may be represented on X, may be represented in this way. So the ideal sheaf of the subscheme of singular points of the fibers, twisted by the pullback of the fundamental line bundle, which implies that, well, the pullback of W of omega B is of course trivial, but also the differentials are trivial. The relative differentials are trivial on a general closed fiber. This implies that if we go to the previous exact sequence, that these two sheaves have the same rank, and the rank is exactly R, right? And moreover, if B is a generic point in the base, closed, of course, what happens is that the restriction to the differentials, under our assumptions, the restriction of the differentials of X to the fiber are all isomorphic to the second Atiyah bundle of the fiber. And then you twist by V, you use the properties of V that we are assuming, right? These two properties. It turns out that this restriction is isomorphic, may be represented in this way. Okay, and then you work a little bit, and you find that also this bundle has a rank R. So if we go to the sequence at the beginning of this slide, in the first two slots, we have two rank R vector bundles. So the co-kernel has the rank 0, and since it's inside the vector bundle, it must be 0. So this arrow here is an isomorphism. Okay, and then taking global sections, we get an isomorphism, the isomorphism of this expressed in this blue equation here. Okay, so we have proved this proposition. If a V is vertical determinant, is semi-stable on a general fiber, and its spectral cover is reduced, then it can only carry vertical Higgs fields. Another structural property we may consider for a Higgs field is that of being scalar. In this case, what we do is that we consider the standard, the canonical embedding of the structure sheaf into the endomorphism sheaf of V. In getting global sections, we get an injection. So in particular, right, we have Higgs fields that are just differential forms on X. Right, oops. And then this proposition establishes a sufficient condition for Higgs fields on V to be all scalar. So we have our vector bundle V. We assume now it is a fiber was regular. So it's a regular on all fibers with vertical determinant, and it will have a spectral cover. And now we make assumptions on the spectral cover, together with some numerical assumptions. Either we assume that the spectral cover is integral, and then we want D to be at least 2G minus 1, or the spectral cover is reduced, then we need a condition on the second Chern class. But in both cases, every Higgs field on V is scalar. G, of course, was the genus of the base curve G. Okay, so again, these are just properties of the vector bundle V, right? The fiber was regular, vertical determinant, and the spectral cover, which is either integral or reduced, and satisfies some numerical condition, which is different in the two cases, right? Then every Higgs field on V is a scalar. And here the proof has some motive of interest because it involves some new structural results about our vibration, the spectral covers, etc. So first, if V's fiber was regular, then you can show that the direct image onto the base of the endomorphic sheaf coincides with the direct image of the structural sheaf of the spectral cover. Okay, then we consider this vector bundle S, right? Similar to S3 that we considered at the beginning to get the Weierstrass model of X. Now we consider the direct image of OX R sigma, where R is the rank of the vector bundle. So we projectivize it. And we also consider this exact sequence, namely, we consider the canonical evaluation map, right, the arrow on the right. And this happens to be surjective. We take the kernel happens to be locally free, and we projectivize it, and we get a projective bundle on X whose fiber dimension is R minus 2. And this happens to be the relative incidence correspondence of the linear systems on the fibers of pi associated to the line bundle OX R sigma, namely restriction to every fiber of this line bundle gives a line bundle on the fiber, so it gives a linear system, and therefore you have a family of complete linear systems on the fibers of our elliptic surface. And this C may be regarded, which is indeed a relative incidence correspondence in this family of linear systems, can be regarded as a universal spectral cover. The meaning, or a possible meaning, of this sentence is the following. So you see in this square diagram here, we always have, independently of V, we have the morphism on the right, phi. If now we have a vector bundle V of rank R, which has a vertical determinant as a semi-stable on the general fiber so that it admits a spectral cover CV, then its spectral cover is basically a base change or a fiber product of a universal spectral cover according to this diagram, where AV is a canonical, I mean, it's a section of our projective bundle, PBS. It's a section which only depends on the vector bundle V. So it is canonical once the vector bundle, has been fixed. So this script C plays this nice role. It's a universal spectral cover. And okay, then here you have base changes. So you have this isomorphism in the last line of this slide, right? Just by base change of the structural sheaf of the universal spectral cover. And then you play a little bit. You start from this exact sequence, which should be proved, but you can do that. You take pullback via our section, canonical section. We make a twist by the differentials on B. We get this exact sequence in the third line. And this has, again, a splitting similar to what we saw in the previous case. And what happens that, you see, we have numerical hypothesis here, and in both cases, the degrees of these line bundle happen to be negative. This implies, you see, when you consider the exact sequence in the first line and take a global sections, you get a vanishing due to this fact, right? Well, not the first line, but the third line. The third line. We get that the third vector bundle here has no global sections, and therefore the two vector bundles on the left have isomorphic spaces of global sections. And since the second space is exactly the space, it's a space where Higgs fields live, we get that these two vector spaces have the same dimension. I mean, H0 omega b, of course, has dimension g, but also this other vector space has dimension g, and they are isomorphic. So this, this is, I was already reading this slide here. Okay, this map is an injection, and the two spaces have the same dimension. Okay, they have all dimension g, because what's written here, right? This has dimension g because we just computed, and the second has dimension g because it happens to be the H0 of the canonical bundle of B, so it has dimension g. And so this map is an injective map between vector spaces of the same dimension, so it is an isomorphism. And therefore, we proved this proposition, okay, which is about the characterization, no, this one, which is about the characterization of Higgs bundles with scalar Higgs fields. Okay, any questions up to here? Because I think I'm moving to the conjecture, to the famous conjecture.
Ugo, can I ask a question?
Sure, please.
So in the slide 14, there is no second Chern class in the characterization. Is it for
in the first? Yeah, sure. Correct. Yeah, yeah. C2 will be non-negative anyway. But yeah, it's true. This is correct. So the second property includes something on C2, and the first doesn't.
Okay.
So the first is just I think it's quite technical. I don't know. Yeah, the first is a condition. The fundamental line bundle must be positive enough. And then the second is, I'm quite sure if we make some computation, it will tell something about C2. I'm sure. Now I don't remember. Perhaps Vito remembers. Okay. Vito should be online. He remembers many more things than I do, for sure.
Okay. Thank you.
Okay. So, no, this is too early. So I hope I have about 10 minutes, right, more or less. So the conjecture. So we already know, so we have a polarized variety, and many proofs of what's going on here are transcendental. So I assume now that we work on the complex numbers, and we have a complex polarized variety, therefore, and locally free from Y could be, I mean, F could be assumed to be reflexive, basically, but I mean, this is really a detail. The important thing is to consider vector bundles. So we have this class, which in principle is in the fourth group with the coefficients in Z. And actually, back in 2004 with Daniel, we proved the theorem. And only later we realized that it was already proved 5 years earlier by Nakayama, not the Nakayama of the Nakayama lemma, of course, and published in a very obscure Japanese journal. Nobody knew about it. We didn't know, but also, I mean, I remember to give talks showing this result, and some people was even kind of surprised by the result. They didn't know about the result by Nakayama. So actually, we proved it. and this is the result about vector bundles, so no Higgs field. And namely, that we have two conditions. The first is that F is a semi-stable, but its discriminant is not only non-negative, it is actually 0 up to torsion. So, I mean, I ask it to be 0 in H4 with the coefficients in Q, say. This might kill torsion. The other condition is that whenever you have a map from a curve to our variety, you pull back the Higgs bundle, the pullback is semi-stable. So in some sense, this vector bundle is semi-stable as a Higgs bundle. I mean, this Higgs bundle, sorry, no. I'm doing the standard case. This vector bundle, it was correct, this vector bundle is semi-stable on every curve in this sense. The two conditions turn out to be equivalent, okay? So in some sense, semi-stable bundles, of course, they have non-negative discriminant. Those which have a zero discriminant are very special. They are a very restricted class, and they are those vector bundles that are semi-stable on all curves. One should also note that the second condition doesn't depend on the polarization. So this means that if a vector bundle is semi-stable and with respect to some polarization and has vanishing discriminant, then it is semi-stable with respect to all polarizations, going through condition 2, which is polarization independent, right? So this is a theorem about semi-stable vector bundles, no Higgs field. And then, of course, I mean, in some sense, guided by the fact that, after all, Bogomolov inequality is also true for Higgs semi-stable, for semi-stable Higgs bundles, even when the underlying vector bundle is not semi-stable. You may ask if the result is true also for semi-stable Higgs bundles. And this actually can be proved in one direction. So if we know the condition 1 is true, then, and then of course F is semi-stable as a Higgs bundle with Higgs field phi, then again, after pulling back to every curve, the pullback Higgs bundle is semi-stable. So we have these two conditions. Now, 1 implies 2. The fact that 2 implies 1, we don't know. And this was the object of a conjecture. So at the beginning, the conjecture was a little troubled. We didn't understand it too well. But then there's a statement, a correct statement in 2008, done also with Beatriz Graniotero. And we know that 1 implies 2, and that 2 implies 1 is a conjecture. And we don't know if the conjecture is true or not, never being able to prove it in full generality, never be able to find a counterexample. But, and this was a suggestion by my former student, Alessio Lo Giudice, why don't we look for, I mean, after all, the conjecture makes sense after fixing Y. So we fix the variety, right? And we try to prove that 2 implies 1 on that variety, on that class of varieties. So we call Y Higgs variety if the implication if the condition 2 implies condition 1. Okay, if the implication 2 implies 1 holds for Y. We call Y a Higgs variety. And therefore, the problem comes of doing some Higgs variety zoology, right? Let's classify them in some sense. And the first quite general result, in some sense, that I found with Alessio is that varieties whose tangent bundle is numerically effective are Higgs. By the way, at least up to dimension 3, varieties with numerically effective tangent bundle were classified by the Mai, Peternel, Schneider, so they are known. So we have a whole bunch of varieties for which the conjecture is true. And also in the paper with Alessio, we also showed that whenever you have a Higgs variety, you have some recipes to construct new Higgs varieties out of them. I don't want to go into details, but we have constructions such as taking fibrations over a Higgs variety whose fibers are rationally connected, or étale coverings, quotients. So there is a possibility to extend this class of varieties in this way. And then for a few years, we were stuck. Back in 2017, with Valeriano, Lance, and Alessio, we proved that K3s are Higgs. So the conjecture is true for them. And actually, sometime later, together with Armando Capasso, we proved that all simply connected Calabi-Yaus in any dimension are Higgs. And actually, the proof is much easier, because the proof for K3s that we found uses quite strongly the structure of the cohomology lattice of the K3, etc. But actually, I mean, it's perhaps a nice exercise, but it's not really needed, because I mean, the problem is deeper. Is just I mean, you just need the Calabi-Yau structure and the fact that it is simply connected. And this strongly relies on a result that we found together with Beatriz, I think, Alessio, and Indranil Biswas, namely the fact that on a simply connected Calabi-Yau variety, projective Calabi-Yau variety, simply connected, if you have a polystable Higgs bundle, then the Higgs field vanishes. Okay, and this is actually the key to prove this fact. The fact that simply connected Calabi-Yaus are Higgs varieties. And this is the last slide. Namely back to elliptic surfaces, and we have this partial proof of the conjecture. So suppose we have a pair of integers, Re, R must be at least 2, and on the other hand, E must satisfy some lower bound. We fit a line bundle mu of degree E on B. Then we have, in a natural way, you remember our fibrations of section sigma, we may consider this linear system, okay? And we consider we take a general curve in this linear system. So this is in particular smooth, and we take a Higgs bundle whose underlying locally free sheaf, I mean, a rank R vector bundle, which has vertical determinant. Second Chern class is this E, so it's second Chern class satisfies this inequality, and the underlying vector bundle is a fiber-wise semistable, and its spectral curve is this. So it has a smooth spectral curve. Then W is not curve semistable, as we should expect, because C2 is positive. The C2 is also the discriminant. Okay, so it is the negation. I never remember how to say it. I mean, it's the second. It's not two. Not one implies not two, but not always, but only when some numerology is satisfied. So it's a partial proof of the conjecture. And then the proof is a kind of combination of stuff that we already saw. Namely, first, this linear series, I gave it for understood a couple of minutes ago, but actually first you have to prove that this linear system is base 0.3, which it is. So you make some checks, you find that this linear system is base 0.3. So the generic element in it is smooth. And then by previous results, in particular involving the spectral cover of a vector bundle, we know that this vector bundle is fiber-wise regular. Then again, because we have some numerology, we know that the Higgs bundle is scalar. You remember, we have a result which some assumptions on the vector bundle, some numerology says that all Higgs fields are scalar. we are exactly in those conditions, so the Higgs field is scalar. Now, of course, what happens, you know, the semi-stability for a Higgs bundle checks the slope inequality only for invariant subsheaves that are invariant under the Higgs field, right? But if the Higgs field is scalar, every subsheaf is invariant, okay? So Higgs semi-stability or semi-stability is the same thing. But the conjecture is true for ordinary vector bundles. And since this has a positive discriminant, then we know that V is not curve semi-stable. But due to the fact that all Higgs fields are scalar, W is not curve semi-stable either. Okay, so we prove that V, script V, which means the Higgs bundle V phi, is not curve semi-stable. Okay, so this is a partial proof of the conjecture on elliptic surfaces. So far, we were unable to prove the conjecture of elliptic surfaces in full generality. Actually, if you look at the varieties for which we were able to prove it, they all have a Kodaira number 0 or negative. So the challenge is to go to positive Kodaira number, so in particular 1. So for instance, elliptic surfaces, and of course it's completely open for say surfaces of general type. Okay, for which I mean, if a candidate for a counterexample exists, probably it is to be looked for in the class of surfaces of a general type, but so far no way of finding one. So I think I will stop here. Thank you very much for your patience.
Thank you, Ugo. Any question?
So
Okay. So which surfaces again are the conjecture is proved on them?
So numerically effective tangent bundle, which includes rationally connected varieties, which includes rational varieties. A billion varieties, and more, of course, but in particular, so numerical effective tangent bundle implies, these are examples of such surface. Then things that don't fall into this category, but they are obtained in some ways out of these varieties. And then next step was the K3s and then Calabi-Yau. For instance, using what is written in the middle, you can prove that this holds for request surfaces, because you know them for K3s, and then using what's written in the middle, you go to request surfaces, for instance. While we didn't prove directly that the request surfaces are Higgs, but this comes from this construction. Yeah, these are this is the zoology we know about Higgs varieties.
Okay. So any other questions? If not, maybe we can thank the speaker.
So, sorry, Amar, I think Daniel had a question as well. Daniel,
well, actually, it was
yeah, well, that was just a comment. Hey, can you hear me?
yes, we do hear you.
Yeah.
Go ahead.
Just a comment. All the result of treatment model written on vector bundles on elliptic surfaces are better understood and greatly simplified by using the Fourier-Mukai transform. as Ugo perfectly know, because we wrote a book with Claudio Bartocci that includes that theory. I have the impression that some of the results you have reported on could be simplified and perhaps improved by using in a systematic way the Fourier-Bouquet transform. Yeah, that's my comment. For Ugo.
I have a counter comment. Of course, we checked that. For the moment, we found no sensible simplification. It's just a reformulation. So, should I write a book about vector bundles on elliptic surfaces? I would cover all possible proofs, but simply we cited the original results by Friedman, Morgan, Witten. Yeah. But perhaps, yeah, of course, you may be right. I should say that I was never able to use the Fourier-Bouquet transform for our conjecture because, as Marcos knows, it's not easy to have a Fourier-Bouquet and Higgs talk between them. No, the Fourier-Bouquet doesn't seem to behave well when acting on Higgs bundles. Then perhaps one needs some less naive idea than just transforming things using Fourier-Bouquet.
My idea is that it provides you a great control on the spectral power and the properties.
I can tell you, Danielle, that I reread all our papers, not only ours, but also what you wrote with Porras. We couldn't find anything more than what we already knew. Of course, this simply means Vito and I. And of course, you are welcome to find new results and collaborate, of course, on that. We can talk about that. That would be nice, of course.
Okay.
Okay, thank you. So any other question? Okay, now maybe we can thank the speaker. Thank you, Ugo.
My pleasure.
Okay, so now we have another 5 minutes for the next talk, 6 minutes. So if anyone wants to take a glass of water and so on, let's try to
Okay. Give me 5 minutes.
So if the next speaker,
Hi.
we want to, hi, nice to meet you, virtually, albeit. It's,
Hi. So
nice meeting you.
Yeah, you too.
Nice to meet you.
Nice to meet you too. So let me test if my iPad works.
Okay.
Amaro, you are recording now,
Oh yeah, let me.
Okay.